Just 3 seconds. Hey, not ready. Okay. All right, so this is the final day of section 2.6, limits at infinity. All right, so we're going to evaluate the limit as x goes to 2 from the right of arc tangent of 1 over x minus 2. Oh, man, I really should have prepared this because this is a hard one. You're like, why is it difficult? Okay, so to do some of these problems, we are going to need to replace the innermost function with a variable. Like, for example, here, what if I had said that t is 1 over x minus 2? T is 1 over x minus 2. Well, then the limit as x goes to 2 from the right of x goes to 2 from the right of arc tan t. Now, if the limit as x goes to 2 of arc tan t, I can actually replace this with the limit as t goes to something. Right? What can I replace the limit as t goes to something? Well, what is the limit as x goes to 2 of the innermost function? What is the limit as x goes to 2 of the innermost function? I mean, could we do direct substitution? No, we can't. But the fact that we know about 1 over x minus 2 tells us that what's happening at 2? Because we know where the denominator equals 0 is either a whole or an asymptote. And so if I want to say what is the limit as x goes to 2, if it's a vertical asymptote, what is the limit as x goes to 2? Infinity. Okay? So what you're doing here is we're evaluating this as x goes to 2 of the innermost function. And we're saying, well, we can replace that with t going to infinity of arc tan of t. Because x going to 2 of 1 over x minus 2 is going to be infinity. I can replace that down below the limit. That's going to be equivalent to saying the limit as t goes to infinity of arc tan t. Now, what is t going to infinity of arc tan t? Well, think about this. Think about it on the unit circle. Now, what am I specifying when I say arctan of t? Why not just say inverse tangent of t? What's the difference in saying arctan rather than inverse tangent? Anybody know? Right. It's that restricted domain. There's only one output, right? So remember the restricted domain of tangent is first and fourth quadrants, right? So I'm only focusing on this with arctan. And I want to say the limit as t goes to infinity. As t goes to infinity. So as I get bigger and bigger and bigger this way, right? That's the limit as t goes to infinity. So what is the limit as t goes to infinity of arctan t? It's going to keep getting up and up and up and up and up. So that means it is pi over 2. Ooh, okay, I want to blue. Okay. Pi over 2. Because as I get closer and closer to the 90, that's going to make it go closer and closer to pi over 2. That's where I'm taking the t, sending it bigger and bigger and bigger. Okay, that's going to make the tangent get bigger and bigger and bigger. The angle, the biggest possible one, is pi over 2. So what did we do here? Well, the process is when you have this kind of like composite type function, what you can do is evaluate the inner function. This is kind of like a new technique here. Evaluate the inner function and kind of change the variable, right? We change the variable. We're saying, okay, let t be this inner function. But then when you do that, you not only have to change this piece in here, but you have to change what the limit is going to. You kind of have to evaluate the limit of this inside piece and say, Well, if we know the limit of x going to 2 of this is infinity, I can say the limit as t goes to infinity of arctan t is equivalent. Okay, let's take a look here. The graph of the natural exponential function, y is equal to e to the x, has the line y equals 0 as its horizontal asymptote. I should turn off the sound. I'm getting emails and stuff. Yep. Like what I said yesterday, horizontal asymptotes are limits at infinity, right? That's where horizontal asymptotes will occur. So it's either rational functions or exponential functions. So this is kind of talking about the other option. We had rational functions and now we have exponential functions. We do have horizontal asymptotes for exponential functions. Like for example, if I talk about the limit as x goes to negative infinity of e to the x, that's saying on the left side of this exponential function, it is going to have a horizontal asymptote at 0. Something that we already know and we've already studied at great length in Algebra 2 and Pre-Calc, that all exponential functions will have horizontal asymptotes. The exponential functions where the base is greater than 1 has a horizontal asymptote on the left. The exponential functions where the base is less than 1, meaning a decay function, the horizontal asymptote is going to be on the right. So how does that change things? Well, we just have to change up this notation. So we can say the limit as x goes to negative infinity, which tells us on the left side of e to the x is 0, because as I increase my negative exponent, or my exponent into the negative direction, right? Well, if I take e to the negative third, that is 1 over e to the third. If I take e to the negative 10th, that's 1 over e to the 10th, and so on and so forth, right? That is 1 over e to the negative 5, 1 over e to the negative 10th, and it keeps going on forever and ever and ever and ever, and keeps getting bigger and bigger and bigger within the denominator, which makes that value smaller and smaller and closer to 0, okay? All right, so let's take a look here. Find the limit as x goes to 0 from the left of 1 over e to the 1 over x. Okay, so this is another one of those composite-like looking functions. So we're going to use that same technique that we did in arctan. We're going to use that same technique here. So we're going to say, okay, we're going to let t be 1 over x. We see the inside function there of 1 over x. Let's let t be 1 over x. Okay, so as I get closer and closer to 0, what's going to happen to 1 over x? What's it going to go to as I make x closer and closer to 0? Think about the graph of 1 over x. And I should say get closer and closer to 0 from the left, right? Correct, I guess I should say. From the left side of 0, what's happening to this function? Where's it going? Negative infinity. So what I can say here is that this is equivalent to saying the limit as t goes to negative infinity of e to the t. Right? Now, think about what that means. If I'm looking at e to the x, or e to the t in this case, that brings me right back to this. What is the limit as I take e in the negative direction? 0. So that means this limit as e to the t goes to 0. All right, let's do a couple more here. Evaluate the limit as x goes to infinity of sine of x. Now, you guys know what sine looks like, right? You guys know what sine looks like. So we're going to investigate, and this is not capital S sine, right? This is just sine. Will it ever converge to one number? Will it ever get closer and closer and closer to one number? Is there ever any horizontal asymptotes on the way out there? I mean, the highest it could possibly get is 1. The lowest it could possibly get is -1. So it's going to oscillate, and that's the term that they use in the book. It's going to oscillate between 1 and -1. It's going to have all points in between, but it's going to keep going forever from -1 to +1. So what we can say here is that the limit as x goes to infinity of sine of x does not exist. Okay, this does not exist. If it ever doesn't converge to one number, and I guess I should be a little bit more specific about that, this is going to oscillate between two values, right? There is a difference between this, because this does not exist. There's a difference between this and when we have some sort of polynomial function, like I was talking about with Mr. Donaldson at the beginning today. That's different, and that's actually what we talk about next. The limit exists here. The limit does not exist here. Okay? The limit exists for polynomial functions because it's going to keep getting bigger and bigger and bigger. The limit does not exist for sine because it just keeps going in between -1 and +1. So how can we write polynomial functions? That's what we're going to look at next. Infinite limits at infinity. That's interesting. Infinite limits at infinity. Well, how can we write this? Well, this is kind of like what I was talking about at the beginning. That statement right there, look, it's right here. If the function, say you've got your parent cubic, which is actually the example down below. Say you've got your parent cubic. We know what the parent cubic looks like, right? Something like that. Ooh, a little bit less shallow in the middle there, but you get the idea. I don't really care about what's happening in the middle because I only care about what's happening as x goes to infinity or as x goes to -infinity. As x goes to positive infinity of this thing, what's going to happen? As I continually make this x value bigger and bigger, the function goes up, right? So we can say the limit as x goes to infinity of x cubed is positive infinity. It's going to keep going up. This is our whole end behavior thing that we learned back in Algebra 2. We just didn't know how to write it like this. We didn't know what that, or now the kids will learn it in Algebra 1. The limit as x goes to -infinity of x to the third, well, it goes down, right? Cubic function, positive leading coefficient, odd degree, positive, negative, positive, up on the right, down on the left, down on the left. See, there's a difference between that and the limit not existing. If it's going to oscillate between values, then the limit does not exist. If it's going to keep going up forever, the limit exists and it's positive infinity. If it's going to keep going down forever, the limit exists and it's going to go to -infinity. There's a difference there. Okay? And this will relate directly back to our end behavior names, right? Positive even, and this is only for polynomials. Positive even, both going up. Negative even, both going down. Positive odd, right arm up, left arm down, which is x cubed. Negative odd, left arm up, right arm down. Okay, so let's take a look here. You know, you might be tempted. You might be tempted to say, well, let's try direct substitution. And say this. Don't write this down. Right? And what is infinity squared? I mean, if you square infinity, aren't you just going to keep going on forever anyway? You might be tempted to say that this is 0. Don't do that. This is not 0. Okay, this is not 0. Analyze the function on the inside. X squared minus x. What's that going to look like? Positive even. Positive even. Up on the right, up on the left. Positive even. The limit as x goes to infinity, that's saying on the right side. On the right side, it goes to infinity. Coincidentally enough, it also goes to infinity on the left side as well. But it didn't ask us about that. It only asked us to find the limit as x goes to infinity. It's not going to converge to one thing, but it's also not going to oscillate like sine did. Take a look at this last one we got here. Now, I would probably rewrite this and say x squared plus x over negative x plus 3. I don't know why. My brain works better that way. We know based on our rules of rational functions that if it's top heavy, which this one is, it doesn't have a horizontal asymptote. Right? If it's top heavy, it doesn't have a horizontal asymptote. If it's bottom heavy, it's at 0. And if it's equal to, the leading coefficients get divided. And that's the situation we talked about to begin this lesson. Okay, so this is top heavy, right? This is top heavy. So that means there is no horizontal asymptote. So what that's telling me is I'm not going to get something like this, x going to infinity of whatever this is equals to L. That's not going to happen, where I'm going to get some finite value. Okay? Because this does not have a horizontal asymptote. So now we just have to figure out what is happening on the end. What is happening on the end? Well, I think the best thing that we did yesterday was divide by the highest power on x. Divide by the highest power on x. So let's do that. Oh. Am I only dividing by x? That's kind of interesting. In my notes, I'm only dividing by x. Oh, here's why. I see it. I wrote it and erased it. If I divided by the highest power on x, so don't write this down. If I tried to do that, because that might be your first instinct. What would I get? Oops. What would I get? Well, this would turn into 1 plus 1 over x over negative 1 over x plus 3 over x squared. What happens as I send x to infinity? Well, that stays 1. This goes to 0. This goes to 0. This goes to 0. Ruh-roh. Everything goes to 0 in the denominator, and I end up trying to divide by 0. So that technique actually doesn't work like this. So if you ever try that technique, and it turns out that everything is going to 0 in the denominator, here's something else that you could possibly do. Okay? So what I'm going to do now is, instead of dividing by the highest power on x, I'm going to divide by the highest power in the denominator, okay? Because they're not equal. So x squared over x plus x over x, negative x over x, plus 3 over x. Okay, so let's take a look and see what happens here. Maybe this is going to help us. So this is going to be x plus 1 over negative 1 plus 3 over x. Now, take a look at what's going to happen now if I send x to infinity. What's going to happen now? Well, this is going to become infinity. I guess I'll just write it. This is going to become infinity. Plus 1 stays. Minus 1 stays. What's going to happen to 3 over x? 0. Okay, well, we can actually evaluate that. Infinity plus 1 is infinity. -1 stays on the bottom, so guess what it goes to? Negative infinity. So if you ever run into a scenario when you try to divide the highest power, try to divide by the highest power on x, and it makes the whole denominator go to 0, because this is what we learned how to do yesterday. Divide by the highest power, highest degree, right? But unfortunately it made the whole denominator go to 0. So what you want to do is divide by the highest power in the denominator, and that will actually do it for you. I could really divide by any power on x if I really wanted to, right? Because all I'm doing is really just multiplying this thing by 1. I'm multiplying this by 1 over x over 1 over x. But that really helped us because we were able to evaluate it. Okay. All right. And I think, nah, we'll stop there. All right.